session. My name is Jan Push, the first Jan, and today I will present the technology we developed for Parser to improve its performance that we call compiler. Basically, I would like to ask which of you have heard the question there? Which of you have heard the statement that parsing is solved problem? Only one. Okay. So, who is familiar with parsing? Not so many people. Oh, okay. Okay. Because usually when I say, oh, I do research in parsing, everybody says, oh, I thought parsing is solved problem. But what I would like to tell today is, this is what I think about parsing right now, and or about the technology behind parsing these days. And I will tell you the story why I do think so and what can we do to improve this. So basically, when I came and started doing some parsing in Paro, we had a project, and as a starting thing, I decided why not to try Petit Parser and parse Ruby. And everybody knows, and I did not know this time, that parsing Ruby is actually a pretty hard thing, and it's not so easy, and the only way how to parse Ruby is close someone into the room for half a year and hope that he will give you a parser and then give him 1 year holiday or something like this. So we thought, okay, maybe parsing Ruby is not the best idea, so let's try to parse Python. Python is significantly easier, but it has this thing, it's indentation sensitive. And actually, it's not so easy to parse indentation-sensitive grammars in general, so it was not possible, even though nowadays I think there are some technologies to support these. So I decided, okay, Ruby is hard, Python is special, let's try Java. There is a Petit Parser Java parser in Moose. It has like 163 commits or something. And if you try to parse the standard library, it will basically fail on 3 out of 10 files. Because there are still features that are not implemented in the parser that are in Java. So basically you cannot even parse Java with reasonable reliability. So the only grammar I found in Petit Parser that was working well was for Pharo, because there was a parser for Pharo. So because of these problems, and I would like to parse more things, we were thinking and how to extend Petit Parser, and we came up with a lot of ideas. Some of these ideas we actually presented here on IWST. And the good news for us was that with these ideas, I'm not telling that we could do this precisely, but we have techniques how to extract with reasonable precision and recall information out of these languages. And we thought, okay, we found cool things and everything is working, and we solved our problem. And actually still, even with this extension, the parsing technology we used was not good enough, because there are some people, and these people care about performance. And if you care about performance, and you will see my changes in Petit Parser, you will be angry. Even though I tried really a lot to keep the performance on a reasonable level, it was not so good. And we were sad, because we were thinking like how to have these features, or how to support powerful features while preserving the performance. And in order to answer this question, we will have to do a small explanation into the parsing technology, etc. So, the thing is, there are several categories of languages or grammars. The first one you know probably well, these are regular expressions. The other category is context-free languages. And you can recognize context-free languages, basically they refer to themselves. So this expression refers to itself here. And there are context-sensitive languages that have more complicated rules. And for example here, it refers to itself, but it also has these indentation rules that happens to be context-sensitive and that you need extra information to this. So, in order to parse context-free language, you need some formalism which is pretty straightforward. It's finite state machine. It's easy. If you have a context-free language, you need to add extra stack, because this stack is used to keep the recursion, etc. If you add yet another feature, you need basically 2 stacks, which is more or less equivalent to Turing machine to parse the languages like this. And this was the state of the art of Petit Parser. This was Petit Parser, before we started, and we could parse this, but we could not parse this. So we were thinking, we added our extensions. The extensions basically meant we added one more step, and we thought, okay, we are happy, we have our solution. But there are some people who don't use indentation sensitive features, and these people stay on this level, and they were pretty angry because instead of using single stack that they wanted, we are using 2 stacks, and it was much slower. But if we use only 1 stack, then we cannot parse some features. So basically we have this, like, what should we use? More powerful formalism or less powerful, but we cannot parse this. So we had these problems. And in general, in literature or in parsing technology, you can find some solutions to this problem. One of the solutions is to create one small dedicated stack only for indentation. And you will use this one, and basically you can parse indentation sensitive languages. But if you want to parse Ruby, there are much more features than indentation that you will not be able to parse. So some people came with different ideas. This idea I just want to demonstrate. Somebody came up with the idea how to parse context-free languages faster. Somebody came with the idea, oh, let's combine these 2 ideas together, so combine 2 different stacks, or somebody came up with another different idea. And here is where the compiler comes. We came with the idea of using 2 stacks, actually not doing this at all. We are not experimenting like what kind of stacks we should use. How this compiler work is that for context-free or for regular languages, we use finite state automata. For context-free, we use finite state automata with 1 stack, and for context-sensitive, we use 2 stacks. And what does compiler do? It analyzes the grammar, decides which of these formalisms is best for the given rule, and use this formalism. And during one single parsing phase, it just switches between these strategies and parses. So basically what Petit Parser compiler is and how does it work? It accepts Petit Parser as input, it does its magic somewhere and produces something like this. And basically the output of this is Smalltalk class that you can store, save, load and reuse. And in order to evaluate our how well did we do, we did a Faro case study. In this case study, we basically take 10,000 methods, I guess, from Faro code, randomly selected, and we compared 3 different parsers. Basically, the parsers that are available and that produce the same output. It's the Petit Parser, it's the Smalltalk compiler, CC, and it's RB Parser. All these parsers can be used to parse arbitrary Smalltalk code, and they produce RB tree, so the output is easily comparable. And what we did, we compared these 3 parsers to our compiled version, and we measured the speed up, time of the parser versus our time. And these are the results. Basically, we are more like 4 times faster than Petit Parser. We are 2 times. Thank you. We are 2 times faster than Smalltalk compilers. The reason for this is the technology behind SMAC. It uses table-driven approach, and this is proven to be slightly slower than top-down approach. And because compiler creates top-down parser, it's faster, and it will be faster probably.
And how does it compare against the native parser in Opal?
Native, that's the RB parser.
Sorry, okay, the other one, the one before Opal.
The old
Yeah.
Smalltalk 80.
Small Petit Parser.
The problem, the Smalltalk 80 parser that is in.
I don't know what's the Smalltalk. I did not measure with that. I don't know. We basically then measured to RB Parser, which is used right now in Faro. All the methods you save are basically parsed with this. We are slightly slower than RB Parser. There's a lot of overhead. What I can say, according to my insight into this, there's lots of overhead in parsing expression grammar definition. It creates lots of objects that are then discarded and created, which creates this overhead. So we did not measure only performance of Smalltalk or Faro code. We did performance on different parsers that we found. This is the Java parser. We have more or less 3 times speed up there. Of course, these are not final numbers because there's lots of room for optimizations and we could not implement all of them. So we focused on one grammar, tried to improve that grammar, and this optimization of course works for different grammars, but we have to focus on all of these. Yeah.
So the number there is the time, the factor by which you're faster than each of these
Exactly.
parsers.
It's like from 2 to 10 basically.
12 in the case of
Yeah,
Python.
yeah. The high number here is caused by the fact that there's a context-sensitive thing, and the original implementation in Petit Parser is inefficient in this because memorization remembers the extra stack, which takes extra time, and in compiler we analyze the grammar and see, hey, I don't need to remember it now, so we save lots of mem copies, etc. So that's the reason for this. And at this point, I would like to conclude the talk. Basically, I want to say compiler takes Petit Parsers your input, produces some class that is equivalent to the Petit Parser, but much faster, and you can get performance that is, in some cases, comparable to hand-written top-down parser. Yeah. Thank you for your attention, and feel free to ask questions.
So we have plenty of time of questions.
I didn't understand the Python thing that is 12 times faster. Is it against the native Python compiler?
No. It's compared to Petit Parser. These numbers are compared to Petit Parser implementation. So if you have your grammar in Petit Parser, we can make it faster.
There was another question, please? No?
I don't know.
Okay. Yeah. Yeah.
Do you have any comparisons against other compilers or other parsers for some of these other languages, or do you just
Comparison against other.
say, for example, conventional Python?
Yeah, it's much slower, but the whole Smalltalk thing is much slower. So basically, I would like to compare to JPython. I can compare to JPython or JRuby, and they are much faster.
So, yeah.
You said like your performance was boosted, and I don't want to judge on that. Do you have use cases that really benefit from this performance boost? Or normally when we talk about compiling some grammar or some code, we have the incremental approach, where we never need to bother about the time because it's only a sub-second thing for few code.
On a bigger level.
So the RB parser that you saw it's called on every keystroke and reparses the whole method.
Yeah, just for bringing up
For the syntax highlighting,
yeah, okay,
for
okay.
code completion.
Understood. Thanks.
There was another question. No? We can gain time, and thanks again. The speaker.